Okay, can you all hear me? I guess not. Hold on, let me,
Yep, we can hear you.
okay, good. All right, so we're going to finish up on our discussion of chapter 9 with a discussion of bond energies, or bond dissociation energies to be more precise, all right? So, as you can imagine, as we said before, a bond is an attractive force between two atoms. And therefore, if you want to separate those atoms involved in that bond, then energy is required, right? So that's basically what the bond dissociation energy is. It is the amount of energy that is required to break 1 mole of a covalent bond between atoms in a molecule in the gas phase. And this is very important, right? So we're talking about the gaseous reaction where a bond is broken up, all right? So we met one example of it earlier in this chapter when we talked about hydrogen, the hydrogen molecule, and the energy required to break that bond between the two hydrogen atoms in that molecule. Oh, wait, what's that noise in the background? Folks, if you're not talking or if you're not asking a question, please mute your mics so that I won't be confused by the background noise, all right? Okay, as I was saying, going back to, so in the case of hydrogen, the amount of energy needed to break the hydrogen to hydrogen bond is 436 kilojoules, right? And that's in the hydrogen, in the case of the hydrogen molecule. And here's another example in the case of the water molecule, where you have the oxygen bonded to two hydrogen atoms. The amount of energy needed to break that bond is 499 kilojoules, all right? In fact, to be more specific, the amount of energy needed to break one of the bonds is 499 kilojoules. And then to break the other bond is 428 kilojoules, right? So as you can see, the strength of the bond as measured by the bond dissociation energy is dependent on other factors. In other words, other atoms being present or absent in that molecule, all right? Now, that leads us to the concept of the average bond energy.
Sorry, I need to get the phone, sorry.
Okay. The average bond energy is the average of the bond dissociation energies for a number of different molecules containing that particular bond, right? So that concept, hold on, that noise is still there. Okay. So this concept, the average bond energy, is necessary because what you'll find is that for a particular bond that exists between different molecules, the bond dissociation energies are different. So basically, in order to get an average of that bond dissociation energies, we have to take into account the particular bond in different molecules and the energy required to break that bond. So that leads us to a table, which I thought wait a minute, where's that table? Oh, this table here. If you remember, we talked about this table with respect to bond length, where we have some energy values here for the particular bonds, right? So as I said before, for the hydrogen to hydrogen bond, the energy required to break it is 436 kilojoules per mole. And by the way, let me just say that these are all average values, right? Taking into account different molecules that contain the same bond. So just to choose some other arbitrary examples, we have the hydrogen to iodine bond. The bond dissociation energy is 297 kilojoules per mole. We have values for multiple bonds, single bonds, double bonds, triple bonds. So for example, the nitrogen to nitrogen single bond, its value is 163. For the nitrogen to nitrogen double bond, its value is 418. And for the triple bond, it's 946, right? And I think we talked about this before, but just in case I haven't, let me just say it again. The bond strength, there's a correlation between the bond strength as measured by the bond dissociation energy and the multiplicity of the bond. So you can see here, for example, going from the single to the double to the triple bonds for nitrogen to nitrogen bondage, you see that there's an increase in the bond dissociation energy, right? So the strongest of these three bonds would be the triple bond, followed by the nitrogen to nitrogen, excuse me, double bond, followed by the nitrogen to nitrogen single bond. And that is a pattern that you'll see right throughout this table when you compare bonds that are single, double, and triple. Everything else being the same, you'll see that the triple bond is stronger compared to the double, which in turn is stronger compared to the single, all right? Okay, so with that said, and I already defined the concept of bond dissociation energies. So based on the table I just showed you, we can actually calculate the enthalpy change of a reaction based on the bond dissociation energies of the molecules involved. So the example that is shown here is the reaction between hydrogen and nitrogen to form a compound known as hydrazine, right? And this is hydrazine right here, all right? And basically, in order for us to determine the bond dissociation energies, well, actually, in order for us to determine the enthalpy change of the reaction, we can use the bond dissociation energies of the reactants and basically subtract the bond dissociation energies of the products total from the reactants, all right? And that is basically what we're going to look at here in this example. So what I'm going to do here is go to my writing pad and let me, okay, so the reaction we're talking about here is N2 plus H2 to form hydrazine, which is N2H4, all right? So to balance this, we're going to need a 2 here, right? Now, what I'm going to do is write down or draw the Lewis structure for each of these molecules so that you can see clearly the nature of the bonds within the molecules. So in the case of nitrogen, it is N triple bond N. There's a triple bond between the two nitrogen atoms. In the case of hydrogen, it's a single bond between the two atoms of hydrogen. And there are 2 of them. Excuse me. And then over here, in the case of hydrazine, it's N bonded to N, bonded to H, bonded to H, H over here, and H over here, all right? So that's important because you need to identify the different types of bonds so that you can assign the appropriate bond dissociation energy. Excuse me for a minute. Okay. I don't know why this is happening now. Okay, so if we go to the table, which I have beside me here, you look up the bond dissociation energies for the different molecules, starting with the reactants. In the case of nitrogen, according to the table I'm looking at here, the bond dissociation energy here is 946 kilojoules per mole. In the case of hydrogen, it is 436 kilojoules per mole, all right? But we have to multiply by 2 because of the 2 here, all right? So that takes care of the total energy required to break up these bonds on the left side of the equation. So let me just calculate this. So 2 times 436 plus 946, whoops, 946. And the answer I got for the left-hand side of the equation is 1818 kilojoules per mole. Okay, so that takes care of the left side. Now on the right side, we have just one molecule, but there are several bonds, right? So for the single nitrogen to nitrogen bond, according to the information I have here in the table, the bond dissociation energy for that bond is 163 kilojoules per mole, all right? And then for each nitrogen to hydrogen bond, according to the information I have here in the table, the bond dissociation, where is that? Nitrogen, okay, right. The bond dissociation energy for the nitrogen to hydrogen bond is 389 kilojoules per mole, all right? Okay, but there are 4 of them. We have 1 here, 1 here, 1 here, 1 here. So we have to multiply that by 4, okay? So let me do that calculation here. 389 times 4, and then I add 163, And the total I got on the right side, total of all of this here on the right side is 1719 kilojoules per mole, all right? Okay, now what you have to recognize is that as far as the reactants are concerned, this is the amount of energy that is needed to break it up. So that would be, the breaking up of a bond would be an endothermic process because energy is required to separate the atoms. On the other hand, over here, these bonds are being formed, and therefore the energy change for the formation of bonds will be negative. In other words, bond formation is always an exothermic process. So therefore, to find the enthalpy of the reaction, that would be equal to 1818 kilojoules minus 1719 kilojoules. All right, and let me do that calculation. 1818 minus 1719, and according to my calculation, this works out to be equal to 99 kilojoules per mole. All right, per mole. And this is therefore the answer, all right? So that's basically how we use the bond dissociation energies to calculate the enthalpy change of a reaction. Now let me say again, right, what I said earlier. This works best for gaseous reactions, all right? So in this case, it works well because these are all gases, even though hydrogen can exist as a liquid, but I'm assuming it's a gas in this case, all right? So if you're talking about liquid or solids or aqueous reactions, then it doesn't work as well. This approach in those situations would at best be an approximation, all right? But for gaseous reactions, this is, this works very well for calculating the enthalpy changes for reaction. Okay, are there any questions? Example.
When you're talking about a solid or a liquid reaction, is there a way to calculate the enthalpy accurately like this, or can you only approximate?
No, you can only approximate using the bond dissociation energies. And the reason why, especially when it comes to aqueous and liquid states, is that you have certain, what's the word I'm looking for? Certain interactions that exist between molecules in the liquid state and the aqueous state that doesn't exist in the gaseous state. Because remember, in the gaseous state, the molecules are basically free to, they're basically free from each other in terms of intermolecular forces, all right? In the solid and aqueous state, that's not the case. And that basically introduces some other factors which will affect the enthalpy change calculations if you're using bond dissociation energies. So that's the reason why in gaseous states, bond dissociation energies work very well in terms of calculating the enthalpy changes as opposed to in gaseous states as opposed to the other states. Okay, any other questions concerning this example? Any other questions? Okay, so that's basically it for this chapter. Let me just see here. I don't think there's anything else. Okay, the rest of this chapter is only dealing with Lewis structures for organic molecules. You can read through that on your own. Basically, it's showing you the type of bonding situations in organic molecules, and that's basically it. So not much there to actually go through. So I leave that for you to read on your own. All right, so we're going to move on now to chapter 10. And chapter 10 is totally dedicated to bonding theory and molecular structure, all right? So in this chapter, we're gonna go into more details about bonding. We kind of touched on it earlier when we were discussing Lewis structures. But in this chapter, we're gonna go into it in a bit more detail because we'll be concerned with not only how atoms are connected to each other, but we'll be concerned with as well how molecules and polyatomic ions, how they adopt certain shapes. And also we'll be looking at how the electrons are arranged in terms of energy when it comes to molecules. All right, so let's start off by talking about molecular geometry, which is what I alluded to just now. So basically, when we're talking about the geometry of a molecule, we're essentially talking about the shape, the type of shape that the molecule adopts, especially in a three-dimensional way, all right? So what you see here on the screen are 3 examples of molecules and their shapes. Now, oxygen is a diatomic molecule, and every diatomic molecule has a shape that oxygen will have, which is a linear shape, right? Because after all, there are only 2 atoms, and there's one straight line connecting both atoms. So therefore, molecules such as hydrogen, oxygen, nitrogen, and the halogens, fluorine, chlorine, bromine, and iodine, they all have a linear shape because they all have just 2 atoms, all right? Now, when it comes to more than 2 atoms, things can become a bit more complicated. And that can be seen in the other 2 examples that you see on the screen. The next example is carbon dioxide, which has a linear shape, right? There is the molecule, the shape of the molecule is such that you can literally draw a straight line from one end of the molecule through the central atom to the other end of the molecule, right? So the carbon dioxide molecule is linear in shape. On the other hand, water, as you can see here, even though it has 3 atoms, just like carbon dioxide, as you can see here as it is drawn, it actually has a bend shape, right? As you can see here, the angle between these 2 bonds here is 104.45, all right? So this begs the question, why is it that carbon dioxide is linear, but water is bent, even though they both have basically the same composition, well, not the same composition, but the same number of atoms present, right? Why is it that the shapes are different? Well, there's a theory that is used to explain this. And this theory is called the valence shell electron pair repulsion theory. And basically, the basis of this theory is that the shape of the molecule or the geometry of the molecule is as a result of the repulsion between valence electrons, especially when it comes to the central atoms of these molecules, all right? So we're going to see how this works in this theory. So before we do that, we have to define certain terms. One term that we're going to define here is the electron group, which is any collection of valence electrons that is localized in a region around the central atom and that repels other groups of valence electrons. We're going to see some examples of this shortly. Well, before we get to the other definition, so therefore, the shape that is adopted by the molecule is as a result of the mutual repulsions that occur between these electron groups, all right? And what you'll find is that the orientation of the electron groups in 3 dimensions, we call this the electron group geometry, all right? Okay, so just to show you the electron group geometries that we'll be dealing with in this chapter, if you have 2 electron groups around a central atom, then the shape that's adopted would be a linear shape, right? And a good example of this would be the carbon dioxide example that we saw earlier, all right? If you have 3 electron groups, then the shape, and well, unfortunately, I don't have a model of the 2 electron groups here among these here. The 3 electron groups, the shape would be trigonal planar, right? So that is this one right here. Over here, we have basically balloons that are being used to as models to explain the 3-dimensional or to show the 3-dimensional shapes of these electron groups. So for the 3 electron groups, this would be the arrangement, right? Would be trigonal planar. For 4 electron groups, the arrangement would be tetrahedral, as you can see here. If you have 5 electron groups, then the shape adopted or the 3-dimensional geometry adopted would be the trigonal bipyramidal. And then number 6, or I should say if you have 6 electron groups, then the orientation or the geometry that would be adopted would be the octahedral arrangement. So these are the different arrangements of the electron groups. As I said before, the linear one is not shown, but if you can imagine it being a straight line arrangement. And there are others actually above 6, but at this level, the limit would be 6 electron groups as far as we're concerned, all right? So these are possible electron groups that we will be encountering in this chapter. Is there a question?
Would H2O be a trigonal planar?
No. H2O would be a bent. We're going to get into that. But in terms of the electron group geometry, H2O would be tetrahedral. All right, we're going to get into that. It has to do with the number of bonding, number of bonds, and number of lone pairs of electrons around the central atom. Okay, so before we get into that, however, we need to talk about what we call the VS-EPR notation, the valence shell electron pair notation. So in different, chemical literature, textbook, whatever, they use different symbolisms. So the symbolism that is shown here in this diagram, the central atom is designated A, right? The E here designate the lone pairs of electrons, while the X's here designates the atoms that are bonded to the central atom, all right? So A is the central atom, E, the lone pairs of electrons, and X would represent the hydrogen atoms, all right? So that's basically the VS-EPR notation that we're using in our notes here in this PowerPoint presentation, all right? So with that said, if you keep this in mind, that makes things easier to summarize when it comes to the shapes of the molecules and using the VS-EPR theory to predict the shapes. So the first type of molecule we're going to look at is one where you have a central atom, and around that central atom, you have two electron groups. Now, as we said before, the electron group geometry is linear, right? Now, the central atom has no lone pairs. So therefore, if you're going to use a VS-EPR notation, this is what it would be, AX2. Now, as a result of that, the geometry adopted by the molecule would be linear, right? And that's because the bonds of the central atom will be repelled from each other to be as far from each other as possible, which means that the most stable arrangement will be this arrangement, the linear arrangement, where the bond angles will be 180 degrees, all right? And an example of this would be beryllium chloride, all right? So in the case of beryllium chloride, you have the central atom bonded to two other atoms. There are no lone pairs on the central atom, so therefore the shape adopted will be linear. And I want to also say that this is also true for carbon dioxide, which I showed you earlier. So let me draw the Lewis structure of carbon dioxide up here. Okay, where is that? Okay. So this is the Lewis structure of carbon dioxide, right? And you have two lone pairs here and here, two lone pairs here and here, all right? So basically, the carbon dioxide molecule is linear because you have two electron groups, one here and one here around the central atom, right? And these will repel each other to be as far apart from each other as possible. So therefore, the bond angle here is 180 degrees, all right? So that would be the adoption of the shape of the molecule for carbon dioxide, all right? And the point I'm trying to make here is that it doesn't matter if the electron groups here are double or single bonds. In the case of beryllium chloride, it would be a single bond here and here. In the case of carbon dioxide, it's a double bond here and here, all right? It doesn't matter if it's a double or single bond or triple bond, the repulsion effect will still be the same. And therefore, in the case of beryllium chloride and in the case of carbon dioxide, the shape adopted by those molecules will be linear, all right? Any questions about that example? Any questions? Okay, so the next in this series we're going to look at, let me just skip all this here because I discussed that already, is where we have three electron groups around the central atom. Now, these electron groups will be arranged to adopt a trigonal planar arrangement. Now, the situation we'll be looking at here is where there are no lone pairs on the central atom, which means that the VS-EPR notation is this right here, AX3, right? So basically, the shape adopted by the molecule will be the same as the geometry as far as the electron groups are concerned, because all the electron groups are basically bonds to other atoms. So therefore, the shape adopted by the molecule will be the trigonal planar, and the bond angles will be 120 degrees. And one good example of this, excuse me, is boron trifluoride, where this is the arrangement. So any molecule that has a central atom bonded to 3 other atoms, and no lone pairs on a central atom, then the shape adopted by that molecule would be the trigonal planar, and the bond angles would be 120 degrees. Now, let's look at another situation where you still have 3 electron groups, but one of those electron groups is a lone pair of electrons. In other words, the VSEPR theory is AX2E, right? Now, the shape adopted by the molecule is defined by the atoms, not by the electron pairs. So therefore, this would be the shape adopted by the molecule, right? Now, you'll notice that when you compare this to this here, right? The lone pair of electrons here is occupying a spot where there was an atom here in this structure, right? So in terms of the electron group geometry, these 2 structures are the same. But in terms of the actual shape of the molecule, as defined by the atoms, it's different. Whereas in this case, the shape is trigonal planar. In this case, the shape is angular, or as in some textbooks, they call it the bent shape, right? Now, because these structures have the same trigonal planar electron group geometry, the bond angles will still be the same, 120 degrees, all right? So the bond angles will still be the same, but the shapes of the molecule themselves would be different, right? And an example of this would be sulfur dioxide, where if you look at the Lewis structure for sulfur dioxide, let me see if I can draw it up here. So for sulfur dioxide, the Lewis structure is this. Right? So basically you have 2 electron groups here, and you have a lone pair of electrons here, right? So therefore the VSEPR notation would be AX2E, right? Which is what we said down here, all right? So therefore the shape of the SO2 molecule will be a bent or angular shape, all right? Okay, any questions about these 2? Any questions about these shapes and electron geometry, etc.? Any questions?
No, I don't think so.
Okay, so continuing. We're going to get to a situation now where we have 4 electron groups, right? Around the central atom. Now the electron group geometry that would be adopted would be tetrahedral. And now we're going to look at a situation where there are no lone pairs, right? 0 lone pairs, which means that the VSEPR notation would be AX4. So therefore this would be the actual shape adopted by the molecule, tetrahedral, where the central atom is bonded to 4 other atoms. That's the most stable arrangement, such that the bonds are far apart from each other. In fact, the bond angles would be 109.5, right? So a good example of this would be methane, and this will be the ball and stick molecular model that is used to represent the methane molecule, all right? So that's basically what happens in the case of a central atom bonded to 4 other atoms where there are no lone pairs, all right? Now, let's move from that to this one, where you still have 4 electron groups. So the electron group geometry is still going to be tetrahedral, but one of those electron groups is a lone pair. So in other words, the VSEPR notation would be this right here, all right? And what you'll notice is that the shape adopted by the molecule would be, as I said before, defined by where the atoms are arranged spatially. And in this case, it would be a trigonal pyramidal, right? Now, the tetrahedral arrangement in terms of the electron geometry will still be the same because you have 1, 2, 3, 4. So if you look at it in terms of the electron geometry, it's still tetrahedral. But remember, the shape of the atom or the shape of the molecule is based on the spatial arrangement of the atom. So that's what we're looking at in terms of determining the actual molecular geometry, which in this case will be the trigonal pyramidal arrangement, as you can see here. The bond angles will still be the same as in the case of the tetrahedral shape because the electron group geometry is still the same. And an example of this would be the ammonia molecule. And over here you have the molecular ball and stick representation of that same geometry, all right? So that's what happens if you have 4 electron groups, one of which is a lone pair of electrons, all right? And then we get to a situation where we have 4 electron groups where 2 of them are lone pairs of electrons, which means that the VACPR notation is this, AX2E2, and in terms of the actual shape of the molecule, which, as I said before, is determined by the three-dimensional arrangement of the atoms, this is it right here. It will be a bent or angular shape, right? Please note the electron group geometry as defined by the electrons surrounding the central atom is still tetrahedral, but the shape of the molecule itself, the molecular geometry, in other words, would be angular, all right? And the bond angle will still be the same because they all have the same electron group geometry. And an example of such a molecule will be water. And this is the ball and stick model representing that shape, all right? Okay, any questions about these? Any questions? Any questions? Any questions?
No.
Okay. I just want to make sure that you guys, are following and understanding what's going on here. All right. So we get to 5 electron groups, right, around the central atom. Okay. Now the electron group geometry is trigonal bipyramidal, and we're going to look at a situation where there are no lone pairs, which means that the VACPR notation is AX5, and this would be the actual molecular geometry as you can see here, right? So this is the shape adopted by any molecule where the central atom is bonded to 5 other atoms and there are no lone pairs. And as you can see from this shape here, it's a bit more complicated than the others that we have looked at, which means that there are different bond angles depending on which bonds you're looking at, right? So for example, I don't know if you can see, I don't know if I can point this out as clearly as I wish, but for example, the bond angle between this X and this X here, that would be a 90-degree bond angle. The bond angle between this X and this X would be 180 degrees, and the bond angle between this X and this X, or this X and this X, or this X and this X would be 120 degrees. So, it's a bit more complicated. There are different bond angles. It all depends on, which two X values, or which two X atoms, I should say, you're looking at, all right? Now, that's what happens. This is all that I've just discussed here is what happens if you have 5 electron groups and no lone pairs. So the next slide will show you what happens when you have 5 electron groups and 1 lone pair. The electron geometry is still trigonal bipyramidal. This time, the VACPR notation is AX4E, and the shape of the molecule will be what you see right here, all right? We call this a seesaw shape, all right? And if you compare what we saw earlier to what we're looking at here, we had an X here, right? So basically to get from the structure that I showed you earlier to this, we simply remove the X from here, leave behind the lone pair, and we end up with this shape, all right? And again, you have different angles, bond angles, depending on which two X values you're looking at. And a good example of this would be the sulfur tetrafluoride molecule. And this is the molecular model representation of that molecule. And then going from here to here, where we have 2 lone pairs, we still have 5 electron groups. The VACPR notation is this, AX3ET. And basically this would be the shape adopted by such a molecule. We call that a T shape. And to get from here to here, we simply remove another X atom. So we could have removed this one or removed this one. We're going to end up with this shape right here, all right? And in this case, there are only 2 bond angles that you'll be concerned with. You can have a 90-degree bond angle, for example, from here to here, or here to here, or 180-degree bond angle from here to here, all right? And an example of this molecule would be chlorine trifluoride, and this here is the molecular model representation for that molecule. And then the next we're going to look at is where we have 3 electron groups, the same number of 3 lone pairs, the same number of electron groups. This would be the VACPR notation. And basically to get from here to the shape for this molecule, we simply remove this X, leave behind a lone pair, and basically we have a linear molecule where the bond angle is 180 degrees. And an example of this would be xenon difluoride, all right? And this is the molecular model representation for that molecule, all right? And those are basically the type of molecules and the shapes that would accompany situations where you have 5 electron groups around the central atom, all right? Okay, so Any questions about any of these? Any questions? Okay, so next we're going to look at, let me see here. Oh, okay. Next we're going to look at is where we have 6 electron groups around the central atom. The electron group geometry for that would be octahedral, and we're going to look at a situation where there are no lone pairs. In this case, the VSEPR notation is AX6, and this would be the shape adopted by the molecule having this arrangement, right? You have the central atom surrounded by the 6 atoms in an octahedral fashion. Again, you have different bond angles, 90 degrees if you're going from this X to this X, or 180 degrees. Actually, going from this X to this X and this X to this X would also give you 180 degrees, and 90 degrees going from this X to this X, right? And an example of a molecule adopting this shape would be the sulfur hexafluoride molecule, and this would be the molecular model representation of that structure, where you have 6 electron groups and no lone pairs, all right? Now, if you have a situation where you still have 6 electron groups, but only 1 lone pair, and that means that the VSEPR notation would be AX5E, then this would be the shape of the molecule adopted. We call this a square pyramidal. And to get from the octahedral shape to this shape, we simply remove the atom that would have been down here and leave behind a lone pair of electron. Excuse me. And all the bond angles in this shape would be 90 degrees. Well, actually, no. And we should make a note of this. There's a bond angle here, which would be 120 degrees. So 90 degree and 120 should be right here, all right? And a molecule adopting that shape, an example of a molecule adopting that shape would be boron pentafluoride, and this would be the molecular model representation. And then we get to this, where we have 2 lone pairs among the 6 electron groups. The geometry in terms of electron groups would still be octahedral. This would be the VSEPR notation, and the shape adopted by the molecule would be the square planar shape. And you can see that you can get it from here to here by removing the X here and leaving behind the lone pair, and that would be the result, all right? The bond angles here will not be 90 degrees. This is incorrect, right? So please make a note of this. The bond angle here would be 120 degrees, all right? And an example of a molecule adopting that shape would be xenon tetrafluoride, and this would be the molecular model representation of that shape. So for our purposes at this level, these are the different shapes that you need to be familiar with. There are others which I won't get into because that's a bit above our scope. So basically you don't need to concern yourself with any other possibilities excepting what we have here, all right? Let me see here. Okay, any questions about the shapes in this case? Any questions?
With the square planar, why would it be 120 degrees? Or did you not say that?
There's no 120 degrees. Square planar. Okay. There's no 120 degrees. There is. Okay. In fact, there's no 90 degrees. Actually, I just realized something. The only 2 bond angles that you observe in this case is 60 degrees right here. Whoops. 60 degrees right here, and 180 going from X to X here, or X to X here, right? But I think I know what you're saying. You're talking about this bond angle here from this X, this X.
Yeah. Why would that be? Why would those be odd?
I think that's. Hold on. Let me see here. Yeah, you're right. Going from X to A to X here, that would be 120 degrees.
Why would that be 120 degrees? They all have the same charge.
Hold on, let me think about this again. Hold on. Hold on. I think it's how it's drawn that's tricking me. I think if it's a perfect square, then they all should be 90 degrees. I'm going to look into this some more. I'm glad you raised that question, but I think they should all be 90 degrees. I'm just deceived by the fact that they drew it as a rectangle where it actually should be a square. If it's a perfect square, then the bond angle, you know, should be 90 degrees, if I'm not mistaken. But I'm going to look into it and get back to you on that one. All right. Thank you for that question. Okay, so what I'm going to do is go back to my writing pad here and just work a few examples so that you get a feel for. Oh, before I do that, let me show you something here. I have posted in Canvas a table. Oh shoot. Oh shoot. Let me stop this here. Okay, so let me go to your course and go to files and go to tables. All right. And no, not that. I clicked on the wrong thing. Let me go to this. Now this is where you get this table, which gives you the different possible shapes and geometries. In fact, this gives you the information more directly in terms of the shape adopted by, let me make this larger. Okay, so let me see here. For the square planar, it's 90 degrees, what we just discussed. Remember what we just discussed a while ago, right? So the shape, the angle in the case of square planar is 90 degrees. All right. Okay. But outside of that, this basically summarizes what we just discussed, right? Now, the only difference between this and what we discussed is that instead of A as a central atom, they use E, right? But pretty much everything else is the same, okay? So this table is what you can look to in order to predict the molecular shapes based on the Lewis structure of the molecule, all right? So what I'm going to do now is go to my writing pad, and I'm just going to do a couple of examples. So let's say you're given, the formula. Okay, I'm trying to choose a good example. Let's say you're given. Okay, I'm just going to use, I'm just going to do this one, IF5, all right? And let's say you're asked to determine the Lewis structure and the shape of this molecule, all right? So if you remember what we learned from the previous chapter, the first step is that we count up the total number of valence electrons, which means that iodine will contribute 7 and fluorine will contribute 5. And we have to multiply that. I'm sorry, fluorine contributes 7 and there are 5 of them. So this gives you 35. So the grand total of valence electrons will be 42 electrons, which is equal to 21 pairs, all right? Okay, so we put the iodine in the middle and we surround it with the fluorine atoms. All right, and then we put the bonding pairs, 1, 2, 3, 4, 5. Then the non-bonding pairs, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have used up 20 of the 21 pairs. So the 21st pair will go here, all right, on the iodine, okay? So that's the Lewis structure. So how do we determine the shape? Well, we look at the central atom and we look at the number of bonding and non-bonding pairs present around the central atom. We have 1, 2, 3, 4, 5, right? Bonding pairs, and we have 1 lone pair. So basically, the VSEPR notation that would apply would be A, X5E, right? So if you go to the table, you look for the structure that has that arrangement, which would be, where is it? Which would be this one right here. The central atom bonded to 5 other atoms and a lone pair of electrons, right? And that shape would be the square pyramid shape. So basically, the answer to this would be square pyramid. And that's basically how you do that one. All right? Any questions about this one?
Nope.
Okay, so let's look at another example. Okay, so let's say you're given, okay, let's say you're given PO3 3 minus. Okay, so in fact, no, let me erase that one. I'm sorry, let me erase this one. I'm sorry about that. I mean, you can do that one if you want to, but I'm thinking of another one. Suppose you're given, okay, why is this? Okay, something is wrong here. Okay, SO3 2 minus, all right? Again, Lewis structure. And shape or molecular geometry, all right? I want you to try this one on your own. I need to go get some water. So look at this one, think about it, try it on your own, and let's see what you come up with, all right? I'll be right back. Okay, folks, I'm back. So what would be the first step?
That would be counting up the number of electrons. There's 6 for sulfur and 6 each for oxygen. And then draw a scaffold for the Lewis structure.
Whoa, hold up. What about this right here?
Oh, yes, and add the 2 electrons in. I forgot about that.
Okay, so the grand total here would be
26.
6 electrons, which would be equal to 13 pairs. And then you for skeletal arrangement.
3, 4, 5, 6, 7, 8, 9, 10, 11.
And then bonding pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, then what?
Then we would add the final pair onto the sulfur atom.
Okay, very good.
And that would be here. I know I've got the table around here somewhere. Ah, there we go. There it is. Let's see. We've got 3 atoms.
We need to calculate the formal charges, remember?
Yeah. Oh, yes. Why would we need to do that?
Well, to get the Lewis structure, to get the correct Lewis structure. So,
all right.
What's the formal charge around the sulfur atom?
That would be, let's see here. The group, the group I think is 6 or is no? Yes, it is 6.
Yep. 6, right?
6 minus half of the bonding electrons, which is 6. Which minus the number of non-bonding electrons, which is 2. So that gives us a charge of +1.
+1, very good. And then what about each oxygen atom?
Okay, for each oxygen atom, group number is 6. Half of 2 bonding electrons, which is -1, minus the number of non-bonding, which is 6.
Mhm.
So -1.
Okay,
each
very good.
of them.
So therefore, the sulfur would have +1, and each oxygen will have a -1 formal charge. Okay, what's the next step?
Well, I guess in this case, what you would do is take a non-bonding pair from. Wait, no, you would take a non-bonding. A non-bonding pair from one of the oxygen atoms and add it.
Like this.
Mm-hmm.
Okay, so the final Lewis structure would be double bond S, lone pair here, double bond O, lone pair here and here. No, I'm sorry, I made a mistake. This should be a single bond. So that should be a single bond here. And let me erase this here to give you a lone pair here. And single bond, oh, this should be a minus charge here. And then single bond O, minus charge. So this would be the final Lewis structure of the molecule, all right? Okay, so what would be the shape? Well, if you look at this carefully, you have the central atom, which is the right? And you have 3 other, those would be the 3 X's, and you have a lone pair here, which would be the E.
Which would be the E.
Right, so what's the shape?
I'm looking at the table here. That would be a triagonal pyramid.
Exactly. So the shape adopted by the sulfite ion would be a trigonal, actually, is the term. Oh. Trigonal pyramid. I know what you meant. All right. And that's it, right? So that's basically how you go from the formula for the molecule or ion to the Lewis structure, and then from the Lewis structure, the geometric shape of the molecule. All right. So that's basically how you do that. Any questions about this? Any questions? Any questions? Okay, let's move along to a discussion of dipoles. Oh, wait a minute. Wrong PowerPoint. What am I looking at? Okay, so now we're going to talk about dipoles and polarity and all that good stuff, all right? Now, basically, we talked about electronegativity before, right? And we talked about the fact that you can have polar bonds based on the extent to which you have a separation of charge based on the difference of electronegativities between 2 atoms involved, right? And we looked at the example of the hydrogen chloride molecule, where the chlorine is more electronegative than the hydrogen. So therefore, the chlorine will have a partial negative charge, and the hydrogen will have a partial positive charge, right? So basically, whenever we have this kind of separation of charge, a bond or a molecule, we say that the bond or the molecule is polar. So hydrogen chloride is considered to be a polar molecule. And there is a term known as a dipole moment, which is a quantitative way of calculating or expressing the polarity of a bond or molecule. And basically, this is the equation for calculating the dipole moment of a molecule. Nu, which is a Greek letter, that's the dipole moment, is equal to the charge in coulombs multiplied by the distance that separates the centers of the positive and negative charge, all right? So that's basically the formula that is used to calculate the dipole moment. Now, let me just say that you won't be using this equation at all, but I just thought it was important for you to understand how it is calculated, all right? And I forgot, what's the unit of dipole moment? If I remember correctly, the unit of, here it is. The unit of dipole moment is the Debye unit, uppercase D, all right? So that's how we quantitatively express the dipole in a molecule or within a bond, all right? One important property of dipole molecule is that they align with electric fields. So if you have some dipole molecules in a container, whatever, and you put 2 electrodes inside that substance, and then you extend that you connect that to an external circuit, initially the molecules will be oriented randomly, right? You know, some will be like this, some will be like that, you know, it will be a random arrangement in terms of how the molecules are aligned. But when you flip the switch and the electric field is generated, then basically the molecules will align themselves such that the negative end of the molecules will be pointing towards the cathode, and the positive end will be pointing towards the anode. And this is the basis for liquid crystals, what do you call it? No, liquid crystal displays that you see, for example, on your calculators, such as the one I'm using for my calculations here, right? Of course, it's a bit more fancy, but basically what is happening is that you have the alignment of molecules according to electric fields generated. And as a result of that, that will bring up images on the screen as a result of the alignment of the molecules, because it turns out that when the molecules are aligned a certain way, radiation will be absorbed in the form of light, and therefore that is a black line that you would see, for example, on your liquid crystal display. So that's basically the basis for that. Okay, so that's one property of polar molecules. They align themselves in the presence of an electric field, right? Okay, now, let's talk about polarity of molecules in particular, right? So, one thing you need to recognize about bonds in terms of polarity, and that is that the polarity that is measured does not only have a quantitative property, right? You can actually have a number along with a unit to represent the magnitude. But it also has directional properties. In other words, the dipole can be directed in a particular way, all right? And that is important when it comes to determining the overall polarity of the molecule, all right? So for example, in the case of carbon dioxide here, right? You have one oxygen atom here, one oxygen atom here, right? So as far as this bond is concerned, the dipole is acting in that direction, right? And as far as this bond is concerned, the dipole is acting in the opposite direction, exactly, because remember we said that the carbon dioxide molecule is a linear molecule. So the result is that you have two dipoles which are equal in magnitude because you have the same oxygen atoms here and here, but they are arranged linearly opposite to each other, which means that they will cancel out each other. And the result is that carbon dioxide will have a net zero dipole, all right? What that means basically is that the carbon dioxide molecule is said to be, and let me write this down here. I'm sorry, non-polar, right? The molecule is non-polar because the dipoles within the molecule will cancel out each other, all right? Now, on the other hand, if you look at the water example here, you have the molecule basically arranged at a right angle, all right? And as far as the dipoles are concerned, for this bond, the dipole is acting in this direction. For this bond, the dipole is acting in this direction, which means that they will not cancel out each other. In fact, the net dipole will be according to the direction showed here by the pink arrow, all right? So therefore, the net dipole of this molecule here is a non-zero value. The net dipole of this molecule is non-zero, which means that this molecule is polar. So that explains why the water molecule is polar and the carbon dioxide molecule is not, all right? So basically to determine, so that's what is stated here. I'm sorry, my writing just got in the way of that. These concepts explain why carbon dioxide is linear with no dipole moment and the water molecule is bent with a dipole moment, and it has been measured as being equal to 1.84 dBi, all right? So that's basically how you can predict whether or not a molecule is polar or non-polar. You have to take into account the shape of the molecule and the resulting net dipole of the molecule as a result of the different orientations of the dipoles along the bonds of the molecule, all right? So you could be asked, let me see here, hold on. Okay, so this is basically a three-step approach for determining whether or not a molecule is polar. You have to use the electronegativity values to predict the bond dipoles, or you can use the VSEPR method to predict the molecular shape, and use a molecular VSEPR theory to predict the molecular shape. And then based on the shape and based on the arrangement of the bonds, whether or not they cancel out each other, you can predict whether or not the molecule is a polar molecule. Okay, so again, let me go to a couple of examples. In fact, let's use this last example here, all right? So we went through the trouble of determining the Lewis structure, and based on the Lewis structure, we determine the shape of the molecule. So you could be asked a third question, and that is what is, or whether or not the molecule is polar. So is it polar or non-polar? All right, that's a question that we're going to look at. So in order for us to answer that, we have to consider the orientation of the bonds and the polarity of the bonds. So you have the sulfur up here, and it's a trigonal pyramidal, which means that you're going to have oxygens down here, and down here, right? Now, oxygen is more electronegative than the sulfur, so therefore this would be the direction of the dipole in each case for each sulfur to oxygen bond. And you can clearly see that in this case, they will not cancel out each other. In fact, the net dipole would be here. So therefore, as a result, we can say that this particular ion is polar. All right? Because the net dipoles, based on the three-dimensional spatial arrangements of the sulfur to oxygen bonds and the dipoles along those bonds, they will not cancel out each other. And therefore, the result would be that the particular ion will be a polar
ion. Wait a minute. Wouldn't so the sulfur atom, it has a negative charge, right?
Yeah. Yep.
It's got so.
But the polarity is based on the separation of charges between the oxygen and the sulfur in each case, and therefore the net. So basically, what it's saying is that the negative charge, the net negative charge for the entire species, will basically be towards the oxygen, which is basically what is the case, as you can see in the Lewis symbols, right? If you look at Lewis here, the negative charges are on the oxygens, and basically, as a result, the sulfur will have a net plus charge.
Yeah, but what about the uncharged oxygen atom, the one that doesn't have a charge?
Well, it turns out, and I think we talked about this before, it turns out that the negative charges here are delocalized. In other words, you can have another Lewis structure. Remember we were talking about resonance?
Yes.
Right. Well, that's what comes into play. They all share the negative charges. So this pair of electrons can come here.
Smears out.
Exactly. So therefore, the negative charges are spread among the atoms. All right. Okay. All
right. So
basically, is what happened. Let's do another example. So let's say I gave you. Let's say I gave you. Let's say I gave you. I'm trying to think of a good example. All right, the nitrate ion. We did this before, but we didn't look at the shape or the polarity. So let's start from scratch. So nitrogen will contribute how many valence electrons?
Sorry, I was muted. It will contribute 5.
Okay, and each oxygen will contribute
6.
Okay, and we multiply that by 3, 18. And then the negative charge will contribute how many?
1.
Okay, so the total here would be 5 and 18, 24 electrons equal to 12 pairs. We put the nitrogen in the middle, surrounded with the oxygens. Then we put the bonding pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we calculate the formal charge for the nitrogen. That would be equal to the group number, which is 5, minus half of 246, minus 0. So this gives you 5 minus 6, which gives you, I'm sorry, 5 minus 3, which gives you plus 2. And then the formal charge of each oxygen would be 6 minus half of 2 minus 6 equal minus 1. So the nitrogen has a plus 2 charge and each oxygen has a minus 1 charge. And then we do this to form an extra double bond to get O double bond N plus 1 charge, then O minus, and then O minus. And if you remember, we said that we could not do this, right? Because nitrogen is in period 2, and nitrogen cannot have more than 5, I'm sorry. Nitrogen cannot have more than 8 electrons on its outer shell, all right? Okay, so the shape, well, we have a central atom A, surrounding 3 other atoms, AX3, and there are no lone pairs. So the shape would be what?
Here, let me see. I got it right here. That will be a trigonal pyramid again.
No, trigonal planar. Trigonal pyramidal would be AX3E.
Oh, yeah.
Okay?
Yes, okay.
AX3 without the lone pair would be trigonal planar, all right? So the next, so basically the actual 3-dimensional shape for the nitrate ion would be an exact triangle, O. So this is a shape. Of course, this is me, my lack of artistic skills showing, but that's a shape where the angle here would be all across 120 degrees, right? So this begs the question, would this be a polar or non-polar structure? Well, let's look at this. You have one dipole acting in this direction. You have another dipole acting in this direction. You have a third dipole acting in this direction. They're equally spaced out. You see what I'm saying? So therefore, what the net dipole would be what?
0.
Exactly. So therefore, this would be non-polar as a result. All right. So that's basically the shape of that molecule or that ion. All right. All right. One more thing I want to point out. Oh, before I leave this, any questions about this example? Any questions? Any questions about this?
Don't believe so.
Okay. So one more thing I want to say before I leave you guys. All the examples we have looked at so far, we have a situation where you have a central atom surrounded by the identical atom. But what if the atoms surrounding the central atom are not identical? Let me give a simple example. So let's say you're given CH4, right? Now that, I won't go through all the steps. Basically, this would be a tetrahedral molecule. So the shape would be something like this. H, 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 and then H right here, right? Where the bond angles here would be 109.5 degrees, right? So that would be shape adopted by CH4, okay? Now, what if the molecule was CH4? Oh, by the way, before I even move on to the next molecule, and I should mention also that this would be a non-polar molecule, right? And the reason why is because each of these bonds are essentially non-polar. The carbon to hydrogen bond, if I remember correctly, carbon has an electronegativity value of 2.1, and hydrogen, if I remember correctly, is 2.5. So the difference would be 0.4, right? So therefore, remember we said that if the difference in electronegativity is between 0.0 to 0.4, then basically we're talking about a nonpolar bond. So this bond is nonpolar, that bond is nonpolar, this bond is nonpolar, that bond is nonpolar, which means that the molecule itself is nonpolar, right? Okay. Now, what if we have CH3F, right? So basically, the shape would be the same. The only difference is that you're going to have a fluorine bonded to carbon like this, right? Same shape, but you have a fluorine here. Now, this bond is polar, right? Because fluorine has an electronegativity value of 4.0. Carbon, as I said before, is 2. I think I have these confused. I think this is 2.5 and this is 2.1. All right, you can check it up and see. In this case, fluorine is 4.0. I know that for sure because fluorine is the most electronegative element. And carbon is 2.5. So obviously that means that this bond will be polar, right? So therefore, whereas this molecule is non-polar, this molecule is going to be polar simply because you have a polar bond here, whereas the other bonds here, here, and here are non-polar. All right? So, that's another additional thing that you need to keep in mind where you have different atoms bonded to the same central atom. Any questions about this? Any questions?
I don't believe so. Not from me.
Okay, here's another example. And I think this is going to be the last example for today. So let me click. Okay, I want to show you something that might, you might find this surprising, all right? You have this molecule here, right? This molecule is known as formaldehyde, which is used for several purposes, including embalming bodies, formaldehyde. It's also used in biology for preserving specimens, all right? Okay, now, again, this bond and this bond are essentially nonpolar, right? This bond, because oxygen is more electronegative than carbon, right? So therefore, the net result is that formaldehyde is a polar molecule, all right? Okay, now I want to show you another molecule, which is structurally similar to formaldehyde, but the only difference is that we're replacing hydrogens with chlorine, all right? Now, I don't remember, I think this molecule is called phosgene. You can look this up, but I think that's what this is called, all right? Now, let me ask you, this molecule is also polar, all right? So polar molecule, all right. But one of them is more polar than the other. Which one do you think is more polar? Let me see if you can figure it out. Which one do you think is a more polar? They're both polar, but one has a greater dipole moment, net dipole moment compared to the other one. So my question to you is which one do you think would be more polar?
Oh, it would be in the direction of the chlorine atoms because they would both be there would be a dipole moment going towards them.
Okay, so you're saying the dipole moment here, and okay, but remember, you still have this dipole moment here.
Yes, but I'm assuming that that is not as strong as the dipole moments together of chlorine and carbon.
Well, let me just say this. Remember, the net dipole is as a result of the combination of all the dipoles within a molecule, right? So think about this. We have no dipoles here, so this is mu equals 0 here, mu equals 0 here, and here we have mu with a non-zero value, all right? But in this case, all these values are non-zero, right?
Okay.
So basically, what's going to happen is that there will be some, what's the word I'm looking for? Okay, let's look at it this way. If you were to add these two dipole moments, the two carbon to chlorine bonds, right? The net result of those two, which would oppose this, right? So therefore, this dipole moment here will oppose this dipole moment here, right? In this case here, you have such opposition because these dipole moments are non-zero value or zero values, so therefore they will be zero as well, right? So the net result is that the net dipole moment for this molecule would be greater. Mu here is greater because this net dipole moment here is not canceled out by any dipole moment here. In this case here, this dipole moment here will be canceled out to some extent by the dipole moments arising from the carbon to chlorine bonds. So therefore, the new value for this is less. compared to,
Oh, you want
see what I'm
us to
saying?
compare them. Okay.
Exactly. You have to look at the overall effect of adding up the
No,
dipole
no.
individual bonds.
I thought you were asking us to figure out which direction the dipole moment was for the second for phosgene.
For phosgene, right? No, what I was asking is which molecule will have the greater net dipole moment.
Oh, okay.
You see what I'm saying? Okay. So basically, yep. You have to be careful. In the case of phosgene, its dipole moment is going to be less because you have this dipole acting here, this dipole acting here, right? So they're basically pulling in three directions opposite to each other, so to speak. And therefore, the net result is that the dipole moment will be smaller compared to in the case of formaldehyde, where there's only one effective dipole moment within the molecule, which is the carbon to oxygen dipole moment. All right. Okay. That's it for today. So let me take roll. Today is the 20th. Okay, so let me get out of here. Okay, so Arias Rios is not here. Barber is
here.
Okay, Barber is here. Cannon, not here. Chang, not here. Chavis, not here. Clark is here. DeGraff is not here. Franklin, not here. Han, not here. Panic, not here. Heron, is Heron here? Yes, Heron is here. Holland is here. Jurgensen, Reese, not here. Rose is here. Runnels is here. Santiago is here. And Smith is here. Okay, good. Okay, so that's basically it. Let me remind you that your test is available in Canvas, so make sure you download it, complete it, and it's due on, I think I set the due date as the, when did I say it? Was it the 24th? I don't remember, but it's there, whatever the due date is, all right?
Okay.
Please remember, complete it in blue or black ink. Make sure that you upload it as a PDF document. And what else? And make sure you write your name on each sheet, please, all right? Okay, so if there are no questions, general questions or problems to be discussed, that's basically it for today. So enjoy the rest of your day, and I will see you guys on Thursday. All right. So
all right.
Take care.
Take care.
Mm-hmm.